You have learned how to construct an exponential of a matrix and how to construct its inverse, the logarithm of a matrix. Now we'll combine the two into Newton's formula of them all, and which I call log determinant equals trace log. So exponential can be expressed as Taylor sum, or it can be written as an Euler product of small increments, successive rates, and taking limit of. And matrix is simply replacing terms in Taylor expansion by matrices, or in product by matrices divided by n, so the elements are small increments. The logarithm of a matrix is a Taylor expansion, and the logarithm is simply replace Taylor by array, no matter how big. And here comes the cutest formula of them all. We call it log that equals trace log. If I take a determinant of a matrix, I can take a determinant of its definition as an Euler product raised to the power n. The term in the product I can expand without the determinant. The determinant of each term in this product is a form 1 over a over n. Consider this matrix where determinant is of unity plus A, which is arbitrary matrix, d by d with entries aij. But n is arbitrarily large, so no matter what this matrix is, I can find n sufficiently large. This is a small correction to unity. And let's compute determinant using minors. How does that work? Writing it out, on diagonal we have 1 plus a1 1 over n, and then we have the rest of this matrix. 1, 2, 1, 3 to 1d. The second row starts with 2, 1, then there is a diagonal term which is a2, 2, but it has 1 plus small correction, and rest is all of order 1n. A third row, similar, until we go all the way down to d row. Now, to compute the determinant, you can use the old expansion by minors rule. So, take top row. Then, for each element in top row, you erase corresponding row and column. So, we start with this guy, erase row and column. We get a determinant of the same form, but it starts with a2 2 over n. The rest is the same. And this is now a factor multiplying this reduced determinant. Now when we erase this row and this column, the second term here, then what's left is a2 1 over n, a3 1 over n, etc. On this side, a2 3 over n. And we finally pick up a term which is a diagonal term, this one. But it's being multiplied by a term from here, which is of order 2 1 over n. So this has a term which is order 1 plus 1 over n, multiplying a matrix of the same form, while this guy has a prefactor 1 over n, and when we start expanding it, there will be always a term of order n. So this one, we just rinse and repeat. We repeat what we just did. Well, for this term, we have something that's order 1 over n squared, so throw that baby out. The next minor is of the same form, and all the other minors except the first one are order n squared, so we throw them all out. What's left? It's a product of the terms on diagonal, which all are order 1 plus a small correction, and everybody else is order n squared. This product, first we multiply all the ones, boom, boom, all the ones. That gives me 1 here. Then we keep this term and multiply all ones. That gives me that term. Then we take this term and multiply everybody else, all the ones. That gives me this term. And finally, to the order 1 over n, the only thing that survives are terms of order 1, 1, 2, 2, 3, 3. All of them add up. The rest is a correction. But this is the definition of the trace of the matrix. So the result is that this number of matrix close to unity is determinant of unity, which is 1, plus the correction of order 1, or 1 over n, which is the trace divided by n, and corrections of order 1 over n squared. Raise this to the power n. We get this to the power n plus the order n squared. This number exponentiated for large n. And look, in spite of what people said in the lecture, there were no sign errors. Everything is fine. So we go on. So we get the formula that says the determinant of exponential matrix equals base of the matrix. Let's call this e to the a, let's call this matrix n. And a is the logarithm of the n. Take logarithm of both sides to bring this trace down. And we get the logarithm of determinant of a matrix equals trace of logarithm. This is true of any matrix, no matter, as long as it's a square matrix, whether it's small or large, whether it has rank 0 entries, God knows what. And it turns out this is a crazy formula that we use over and over again in statistical mechanics, in quantum mechanics, in quantum field theory, and in the theory of chaos and turbulence. Very useful formula.